Hey, so this is the rest of that chapter 4 homework. So it's general chemistry for chapter 4. And just as a reminder, I have never actually used a laser pointer. Sweet. Just as a reminder, we were talking about this, how they get the triple bond. And they already have this one bond here. And carbon, of course, isn't happy because it doesn't follow the octet rule, so it doesn't have 8 electrons on its most outer shell. And so it wants this spot, and it connects with one of oxygen's extras. It has another spot it's missing, so it wants another one of its extras. And that is how you end up with this triple bond. And then these two won't bond together because they're happy, they're partners, they're buddies, all of that. And so that is how you get the lone pairs on these two here. So, similar concept. Okay, carbon likes having its 4 electrons here, and then with the hydrogens adding onto it, and that's how you get the single bond. Now, we already know this here, I believe it's sulfur. Let's double check. We have, yep, sulfur here. Okay. And so we have it bonded to its hydrogen. And it has the one lone pair and the second lone pair, because this other one is bonded to a carbon that is already full. And that is how you get the 2 lone pairs here on the sulfur. Okay, so we have our oxygen that we were talking about. It has the 3 hydrogens. So you get the 1 bond, 2 bonds, 3 bonds. However, to follow the octet rule, you have the 1, 2, 3, 4, 5, 6. It has 6 electrons in the most outer valence shell. And so, of course, that makes a bond, a bond, a bond. And you can put 2 of these together to make an even bond out here. However, you have this 3rd extra one over here, and that is how you get the plus. So the way to write it would be you draw out the structure. It has that bonus pair. And then what you would do is you would put the brackets around completely. And because it's an extra one, it would be plus. Because when you have more, if you have an extra electron, it's going to be a plus. If you are missing an electron from that lone pair, then it would be a negative. Okay, and this is another example. This is where we left off. So we have this drawing up here. That's what was given to us. And then, so we put the biggest one in the center, the nitrogen. We have the carbon and a carbon. Well, we already know those 3 each are connected to 3 hydrogens. And then we know with nitrogen, actually going to add it in here to make it easier. So give me just a second. Okay. So that way I can actually show you on here. We went to the car show. Come on. Thank you. So we're going to need this table for later, so don't worry about it right this second. This one is going to be important later as well. And we'll come back and reference it as well. But this is the one I want to look at right now. So, our nitrogen here. Oops. Our nitrogen here. You find it over here. And if we go with the groups, it would be that 1, 2, 3, 4, 5, 6, 7, and 8. So we know our nitrogen is here in the 5 group. So it wants 5 electrons. So then we know that we would have the nitrogen. Well, we know 1 is bonded to a carbon, 1 is bonded to a carbon, and 1 is bonded to a hydrogen. So right there is that 3. And then you would have a 4 and a 5. And that's how you get this pair here. I actually think I might have done that wrong. Nope, it is that 5. Sorry, I'm also reteaching myself Gen Chem at the same time I'm doing this. So we, of course, have our nitrogen. And we have the 2 in the most inner shell, which also can look like that. So then, that takes care of the 2 out of the 7. So then we have that 1, 2, 3, 4, and just for easiness, we'll put it down here for 5. So we have it with a carbon, a hydrogen, and then you have that 2 lone pairs. And that is how that connects there. Okay. So this is going to be coming up very soon in the homework as well. A way to write this kind of a concept is you of course have the 2 groups here, the CH. There's 3 hydrogens. So let's get used to the 3. Now, there are 2 of these that are the exact same, connected to the exact same atom, molecule, anything that's the center. So what you would do, much like an exponent kind of a thing, you'd do the CH3, you put the brackets around, and then you have 2. So you know there's 2 of them within the whole structure. Now, to make it easier for you to understand, this nitrogen is what is directly connected to this group of 2. And it has a hydrogen coming off of it. However, typically the way you would write it is you would have the bigger atom in the front, then you would have whatever extra is also coming off of it, as long as it's a hydrogen, because that is the only one that could bond to this and still leave this open for more. So then this is bonded to that group CH3 twice, and that is how you can get a structure like this. Okay. So I wrote down all of these problems, and we're going to be working through them. So, what it wants here is to take these here. It's showing you where all of the bonds are with these here. And it wants you to turn it into a structural formation that is also showing like the bonded electrons and the lone pair. So basically it's just showing where all of the electrons are, and in this case moving it to something like this. So we're going to start with our nitrogen. That makes it the easiest. Now we know we have one, and we have two. So that means it's going to be a double bond. We're going to have that oxygen over here. And as we can see, there is nothing coming off of these two. So that gives us our two lone pairs. Now, we know this one has a bond, and this one has a bond. So then we can do the one bond, since there's only one set of electrons. And it's not to a nitrogen, it is to an oxygen. And we can see that it's connected to a hydrogen. Now, going to the lone pairs here. Oxygen, of course, once they're focused on their octet here. And then nitrogen, as we learned earlier, that is a 5 when you do the 1 through 8 counting. So of course we want 1, 2, 3. We get this 1, 2, 3. So then we want to add our 4 and our 5. Okay? So moving on to this next one. We have 3 pairs here, so we know it's going to be a triple bond. And the nitrogen has these 2 extras, because 1, 2, 3, 4, 5. And then of course carbon, that's connecting and only having that set of 4. And because this one is triple bonded, we know it can only have one other one and not a hydrogen, since it's connected to this carbon. So what it ends up looking like, we have our carbon, we have our triple bond, we have that extra lone pair. Then of course carbon has its 3 hydrogens connected. And there's that one. So now, in the case of this one here, there's only one bond here, and no bond for these ones. So it's actually fairly simple. Just the hydrogen to the fluorine, I believe. And then because there's no bonds with those 3 other, you get 3 pairs of lone pairs. And that's how you do that one. So now these ones here, the 4.53, it's having us, this is the condensed written out form. It wants us to draw a Lewis structure based off of it. So, the cool thing is, we'll know from this order how it all connects. And as you can see with that concept we used with the nitrogen earlier, you can see that this carbon is not only going to be connected to this oxygen over here, but it's going to have a hydrogen. And then it's going to be connected to a CH3 and there's 2 of them. Okay? So in this case, oxygen is our biggest atom. So we're going to start off there. So we have our oxygen. Okay? And because it has just a carbon and a carbon, there's no hydrogens connected to it, we know it's going to need, or show that it's positive or negative, we know it's going to have its so it's going to be a balanced one. So like here's oxygen, and it's going to have 6. Okay, oxygen is usually most happy when it has 2 lone pairs and then 2 kinds of bonds. Okay? So that's just the common with oxygen, is it's happy with those 2 sets of lone pairs and 2 bonds. Okay? So, here's our oxygen. And then because it's a carbon and a carbon, we know that it can either be like this, and then we would have the rest of our groupings. Or it can go like this. And in this case, we know this carbon has 3 other bonds already through that. Okay, and then we have this extra carbon here. It has to connect to this carbon. Okay. And it only is connected to the oxygen otherwise, and to another carbon. So it's a little confusing. So we will start, we have very end our caboose over here. Just for easiness, I'm going to write the H3 for right now. Ooh. That you may not be able to see. There we go. Okay. For easiness, H3. Then we have a CH2. Excuse me, sorry. Okay, so this one has its 4. So it's all happy. And this one has its 4. So it's going to be happy. So it's connected to this carbon here. Okay, then we have our oxygen, which is right here, another carbon. And then this one has a hydrogen. I'm going to do this in a different color, just so you can see. So a hydrogen. And this particular carbon right here has 2 groups and a hydrogen. Okay, that's important, because if we do it that way, then we can see that's 1, 2, 3, 4 connections there. So that makes this carbon happy. However, what about this carbon? It only has 1 and 2. So it's missing the other 2 connections. So it's not happy whatsoever. So then we know that this portion here has to be changed. Okay? So of course we have this carbon over here. It's all the way over here. We have 1, 2, 3 groups. We have our CH3, our CH3, and our extra hydrogen. Okay? So we need this 4th grouping here. But it can't be with oxygen. And our oxygen still needs its 2 bonds as well. So that is how we get the double bond to satisfy oxygen. And then to connect it all together, what we can do is 1 bond here. And then of course, this carbon has the CH2 and the CH3 over there. So now if you look, this one has all 4 bonds, and so does this one. And that's how we can get from this kind of thing down to here. That way it's satisfied by all of them. Now, in the full answer, what you want is to actually have it all drawn out. So you would have your C. Don't want brown. You'd have your C, your 3 hydrogens. Go to your next carbon, 2 more hydrogens. You have your carbon with your double bond. Then you have this carbon here that has a hydrogen. And then it has your 2 other CH groups. And just because I'm running out of room, I'm going to put it off to the side there. Make sure you can tell that those aren't connected. And so this here would be your final answer. Okay? So, moving on to this next one. We see we have the 2 oxygens here. So that's where we always start, because it's easiest to pair it up that way. So we have an oxygen, and we have an oxygen. Well, you know this second one has this group here. Okay? And we know the first oxygen has a carbon, and then that carbon has the rest here. Okay, in this case, we can connect the oxygens here, and we would get the right kind of answer for that. But don't forget, this carbon still needs to be satisfied. It only has 1 and 2. It needs at least 2 more. So what we can do is actually break this bond, give this one a second one, and then we can connect it to that. In this case, you have the 1, 2, 3, 4 for this carbon. This oxygen is still happy with its 2, and now this oxygen is happy with its 2. So we make it into that double bond, so everything gets satisfied. And to make it nicer looking, so we would have a carbon in the double bond. That carbon's connected to that oxygen. That one has its carbon and its 3 hydrogens. And then we just have the rest of this over here. The carbon, and then the end carbon. And then you just fill in all of the hydrogens. And there you go. Okay. With this one, we know how many our oxygen needs. We know how many our carbons need. However, we don't know how many bonds this chlorine needs yet. So what we do is we go back up to our table, and we can find our chlorine right here. So it has 7 electrons that it wants. Okay. So we'll just jot those down. We know 4, 4, 2, 4, 7. Okay, and that's what would make all of them happy. The easiest way to start is this oxygen. Typically, if you have an oxygen in there, it's easiest to find that one first, because then you can figure out if you need a double bond or a single bond here. Okay? So, we have our oxygen. It is connected to our carbon over here, and is connected to that last caboose carbon. Okay? And with the way this is written, we know that the oxygen is going to be connected here to this carbon. Okay? And then that has its 2 hydrogens. And then we know it's going to connect to that chlorine. And to keep this carbon satisfied, it can only have that 1 bond. So in this case, you don't have to show it, but this would have a bunch of lone pairs over here, and would also be more of that positive side of the atom, and would most likely be like a donator. Not a donator. Yes, a donator. It would be a donator. And so it would be the spot where a negative atom would most likely meet it. So we just leave that chlorine over here, and we just keep that in the back of our mind. So at this point, we don't need to know it, and we're just learning it. And then you just fill in the rest of your hydrogen. Ooh. Okay. So, moving on to 4.55. It wants a Lewis structure. So this here is considered a Lewis structure. So in this case, we have our sulfur. And we know this sulfur is connected to the fluorine? No. To whatever the F is. And there's going to be 6 of them. Okay? So again, going back to a periodic table. No, I was right. It was fluorine. You know, fluorine's going to be a 7. And our sulfur is a 6. Okay? So, sulfur like 6. 1, 2, 3, 4, 5, 6. There's 6 of the fluorine. 1, 2, 3, 4, 5, 6. So our sulfur is happy. And all of our fluorines are what's connected to that sulfur. And in this case, we would most likely have a bunch of lone pairs. Like 1, 2, 3, 4, 5, 6, 7. So as you can see, all of this fluorine is also happy. Okay, we know that it has these lone pairs here. And because they're all paired together, it makes it happy. And that's your 6. And then you have the 7 right here that connects to this sulfur. And the sulfur ends up with the 6. And so it is also happy. However, with Lewis structures, we actually don't write any of the dots. You just kind of got to know that they're there. But this here would be your final answer. Okay? Same thing with aluminum and chlorine. Easiest spot, aluminum, because the chlorine's connected together. And it's going to look sort of like a triangle. Since you have those 3. Now, checking back on periodic table. Over here is our chlorine. The same thing as fluorine with the 7. And then aluminum is right here. It only wants 3. And so, it is satisfied with that 3. And then these will become even because you have the 1, 2, 3, 4, 5, 6, and 7. So this here would be your final answer. Now, we can see this carbon is connected to this. So we have a carbon connected to the sulfur. But as you can see, this carbon is not happy. It only has the 2. Doesn't have the 4. And we know from this first problem that sulfur likes to have 6. Okay, so what we can do is a double bond. That makes our carbon happy. It has the 1, 2, 3, 4. And then sulfur has 2 of its 6. So the 1, 2, 3, 4, 5, 6. And so with those 2 being pairs, then the sulfurs are happy on both sides as well. And that's how you get that answer. Accidentally wrote that one and not the correct one. So this is that S4. Okay. So we know it's going to be connected to this one here. So we know it should be selenium, something like that. And we have the 4 fluorines. Now, we know the fluorines like 7. So 1, 2, 3, 4, 5, 6, 7. So all the fluorines are happy. Let's go check to see if this one is happy. So we find it here, and it's a 6. Okay, so it only has 1, 2, 3, 4. But there's nothing else in this formula either that it can connect to. So then we know it's going to have a lone pair. And in this case, whenever you have a lone pair, this lone pair on something, it's basically going to push these 2 away from it just because of how big this charge and area that it takes up. So that's more like more in-depth kind of Gen Chem or going up to organic chemistry is knowing that. But that is why these would be moved over. Okay. And then just to keep it like a square, we have that lone pair. We're going to have these other 2 because it likes having this line. And so, of course, that pushes the other 2 into this angle kind of a shape to be able to keep this line and push everything else over because of that lone pair over here. Now, this one had a side note. So this, goodness gracious, how about we put do not disturb on? So we stop getting all of those add-ons. Okay. In the case of this, it does not follow the octet rule. It's one of the few weird ones. In some cases it does. You can see it's over here. Beryllium. And it has 2. Okay. And a chlorine here is that 7. Okay. So, we know our beryllium. Each one's going to have chlorine. And in this case, we know this one only lets 2. 1, 2. And chlorine likes to have that 7. So it has that 1, then 2, 3, 4, 5, 6, 7. Okay? And so the chlorines are happy as well. I don't know why your teacher has it on like that. I think just because of the way they're teaching it compared to the way I'm teaching it to you. Because technically, this bond here would technically have an empty spot for that chlorine, so it can connect together and share it with the beryllium. And so that's what he or she means by the not following the octet, because you'll have the 7 spots out here. But if you just think about electron pairs being happy, like I've been showing you, you'd have that 1, 2, 3, 4, 5, 6, and those are all happy because they're paired together. And then you have that 7th here that is happy because it's in a bond. And that makes this one happy because it has 2 of them. Okay? So if you think of it in terms more so with that electrons being happy, it can help when you have these funky octatual ones. Now, our oxygen, we know it likes having 2. And our nitrogen, we can go up and check. Our nitrogen likes 5. Okay? So, we know we have these 2 nitrogens. And the way it is written together, it most likely shows that our nitrogens here are going to be together. Okay? And now, we have our 4 oxygens here. Okay? Now, we could put them all on one. And that would make then this one nitrogen happy, but this one is then missing a whole bunch of electrons and is very, very unhappy. And if you remember, because this one can only take 5, it can't do another oxygen bond here. So all of these oxygens are going to be very unhappy and very unstable. Okay? So what we could do instead is we're going to give an oxygen and an oxygen, an oxygen, and an oxygen. Okay? So right now, our oxygen's only half happy. And this one's only half happy. So, we can do double bonds here. Okay? And then that's going to be the end for these 2 oxygens. Now, this is the hard part, unfortunately. A lot of atoms don't like having 2 double bonds coming off of itself. But it will take a whole bunch of other extra electrons, single bonds, that kind of a thing. It doesn't like having 2 of these double bonds. especially if it's connected to something else, because the way it would bend in its shape does not work per se. It's like two triangles basically, and they're bouncing and pushing the energies off of this oxygen and this oxygen together, and it makes it super unstable. Okay, the energy fields, the energy that this gives off is really big, along with this one. And because of the way the double bonds work, you would have to put the other set of double bonds down here. And that is too close for the oxygens to be together. Okay? So these already don't like each other. That's how you get this triangle pointing away kind of shape. And to keep it from forcing itself back together and having more energy bouncing between two more double bonds, and remember, this nitrogen doesn't like more than one set of double bonds. What happens, get rid of that, is you're actually going to get these extras here. See, so you have the 1, 2, 3, 4, 5 for each of the nitrogens, but not this oxygen. So we know it likes 2 bonds, 2 pairs, and so we have an extra one here for that other bond it could have done. Okay? So in this case, it has 1 extra. That's what it is. Okay? And in this case, you also then have to look at octet, okay? Because it doesn't have this extra bond here, or another bond over here, it's going to have this other sort of electron floating around, that kind of a thing, to help keep it stable. Because remember, we need that 8. Alright? And so we're missing 1 right here. Okay? And so we get those. Okay? Because it doesn't have... Sorry, I'm trying to rethink as well. Because we're not doing another bond, so we know that these are going to be over here to help make the oxygen happy. So we have a 1, 2, 3, 4, 5, 6. And we only have 1 bond, which is 7. Okay? It's not sharing one of these extra electrons here. And so it has basically an extra electron that's not getting shared over here, because remember, there are 2 here, and that oxygen is actually sharing with those 2. Alright? But it leaves us with that empty one. This is very confusing. I know, I'm sorry. So in this case, we would have, we'll move over to the nitrogens. It has that 1, 2, 3, 4, 5. But because it doesn't have its buddy, it's going to make this one positive. Same thing with the other nitrogen. And this oxygen, because it has less electrons than the octet, because it only has that one here, and then it is going to be a negative. That's how it is. Okay. Sorry, it took me a roundabout way to get there. So this one has that extra one because the one's 5, so it would become that positive. This one is missing one to make it happy, and so that is how we get that negative. Okay? Because we got to remember it doesn't have that electron there. It's having to share that other electron. Most of it is based off of this nitrogen though, having that single lone pair here, making it that positive, and this oxygen not having anything else, a negative. So it is just a thing to know and memorize for oxygen because we see it so often. Whenever an oxygen looks like this and something over here is connected to it, we know that oxygen is going to be negative. Okay? Because it doesn't have that other bond to connect to it, and so it doesn't make it very happy. So that's just kind of a thing you got to know in that case, and especially remember that for oxygen since we do see it so much. So, and in this case, he wants you to show the lone pairs. You don't need them on the nitrogen because they're single ones. And whenever you do a plus or a minus near something, so you don't get confused that that minus is possibly another connection, what you do is you just circle it. Okay? So this here would be your final answer. Okay. So moving on, 4.59. We know carbon exits 4. And then what we learned up here with the chlorine, it exits 1, 2, 3, 4, 5, 6, 7. And that makes it the most happy. Okay? So we know our carbon is connected to another carbon because it's 2 before it's connected to the chlorines. Okay? And in this case, like how we discussed with this one and the way it just bends, the easiest way in this case is to have 2 fluorines to each carbon. So you get this kind of a shape. Okay. And that helps keeping these carbons happy, or at least. And these chlorines are very happy. Now, as you can see, these ones only have 3 connections. So, another way to do it is you get that double bond right here. So now each carbon has its 4. The chlorine has its 3 sets of lone pairs, so that's 6. And its bond makes 7. So, in this case, what kind of carbon-carbon bond does it make? It makes a double bond. Alright. So, 4.66. It wants the shape that you get. So, basically what it would look like. And then either how the molecule is shaped or the electrons are shaped. Okay. In the case of a molecule, say it's like bent, it just means you get this sort of like Y shape. That's typically due to having electrons somewhere else. Okay? But you get the tetrahedral shape because there's 4 connections. It doesn't matter how they're laid out, because you have that 4 connections to that center one, you get tetrahedral. Okay? So, doing the psyllium and the fluorine. We know psyllium is going to be in the center. Ooh, too big. Psyllium. In this case, we know the fluorine has 4. Oops. Okay. The fluorine's going to be happy because it has its 7. We can double check our psyllium. Yep, the psyllium. The one's 4. So it has that 4. And the fluorine's happy. And so we get this sort of cross, square, diamond kind of shape. So if we look, this one has 4 connections. And it is just looking mostly for the amount of connections here compared to what the molecule does, okay? Your professor wants this portion, okay? So, with the 4 connections, we know it would be tetrahedral. Okay. This one's a little bit harder because you could do it as this. You could do it as this way. But you gotta remember, it doesn't make them happy. It doesn't make these guys happy either. Okay? Both fluorine and chlorine want its 7. So it likes having only one bond and the rest of its electrons free. So the easiest way is we have a carbon. There are 4 of the molecules. Okay? We have the fluorine and a fluorine. That covers our 2. And it has all 7. It only has that one bond. So our fluorine's good. Okay? Good. So our chlorine would be in the 2 other spots. And again, it has that 7. Only that one bond. And so, and there's 2 of them, 1 and 2. So that one's good. And now, with that carbon, we have our 1, 2, 3, 4 bonds. So, we have a happy structure right there. And, with it having the 4 connections, we're going to know that it's tetrahedral. Okay? So moving on to our sulfur trioxide. Something like that. We have our main one here. And we have our 3 oxygens. Okay? We're going to have our sulfur. And our oxygens. Now, if you remember, our sulfur likes having that 2 bond or having that full 4 bond kind of a thing. To have a fully octet. So you can either make it happy with its 2 bond or its full octet. In this case, what we're looking at is for the oxygens. Okay? We know oxygen wants 2 bonds. However, sulfur can only do 4. So we can at least bind it to 1 oxygen here. And that will make this oxygen happy. But of course, this one is missing 1. Okay? And we know when an oxygen is missing its 2nd bond, it is going to make it a negative. Okay? And so that is how you would draw this one. And its shape, because this center molecule, yes, it has 4 bonds, but in this case for shape, this counts as only 1 bond. Okay? It's only bonded to 1 item over here. Bonded only to 1 item over here, and bonded to only 1 item over here. So, you would actually get your trigonal planar, because it is in that triangle kind of shape. Okay? So, our boron and bromine is next. With this 3 being over here, and it's connected to this one, we know that's the center. And in any way, like we did up here, to make them all happy as much as possible, we know we could do it here, or here, or here with any of them. However, we can see that that boron is only going to be connected to 3 things. Doesn't matter if it has a double bond, a triple bond, whatever. It's only connected to those 3 things. So we know we're going to have trigonal planar. Okay? And we can go double check. So, we have a boron, which is 3 anyway, so it's actually happy. And then we have our bromine, which is 7. So if we go back down, well, our boron's happy, 1, 2, 3. And our bromine's happy, 1, 2, 3, 4, 5, 6, 7. So there's no extra electron clouds we need. The extra electrons. There's no plus or minuses or anything because they're all happy. Now this changes when we get to this NF3. Okay? We know that 3 and that N. Now, when looking at our table, we know this fluorine lacks at 7. And it's 7. And it's 7. So the fluorine's happy. But our nitrogen here doesn't. A nitrogen has 5. So if it has 5, we have the 1, 2, 3. Then we know 4, 5. Okay? And in this case, now everything is happy. Oops. Everything is happy. We know this makes it happy as well. And because we don't have a plus or a minus up here, we know it has to be completely neutral. So we know it has to be connected to that extra pair. So for the shape, it's bonded to 1, 2, 3 items, but it has a 4th item it's bonded to that it could possibly join. So this also will count as one of those bonds for shape. Okay, so we actually have 4 connections here because a 4th thing could connect here. So in that case, we know we have tetrahedral. All right, 2 more pages. So we have a polar and nonpolar. Okay. So polar is an unequal sharing of electrons. That's the positive side. Or a negative side on each side. Okay. Then nonpolar. Equal sharing of electrons. Okay. I have some examples up here. Okay. So we have our water. And remember, this oxygen has those 2 other groups. And then we have our hydrogen. Now, in this case, hydrogen has its one, and its one, and its one bond. So this is happy. It's sharing its electrons, they're good, they're buddies. So that would be nonpolar. This one here, the hydrogens are pretty happy and everything. Oxygen is happy, but these electrons here are much, much stronger than a simple hydrogen. Okay? And it is based on its electronegativity. So, as you are going across periodic table from table 1 to table 8, you're going to get more and more negative. So over here is going to be your positive, and over here is going to be more negative. Okay? And as you're going up, it's the same kind of concept. More negative up here, more positive at the bottom. So we can see over here, these are going to be our most negative kind of buddies. They're not going to share very well. They want to take all of those electrons for themselves because it's missing. It has, I said that wrong, sorry. Because it has that extra electron that it wants to get rid of, because it also has more spaces, it's going to be that negative. Okay? And in this case, these ones over here, they typically are missing their electrons, and so they're typically that positive. Okay? So this would just be a good side note kind of a thing, because that will help determine where it goes. Okay, so based off that chart, we know hydrogens are more likely to be positive and oxygens more likely to be negative. And in any case, when you know you have these extra electrons, automatically, typically these electrons are going to be much bigger cloud kind of a thing compared to the small itty bitty baby cloud. And so you know that the side with the more electrons is going to be more positive. So the way we write that is it's like you're drawing an 8, but you don't make it past to do that last loop. And then you would just write what kind. Again, that weird 8. And oxygen is more negative. Okay? But hydrogen is equal. Because they only want the one. They have its one bond. So it's equal. Okay? And the concept of carbon and oxygen. Okay? If you remember, on that table, oxygen is more negative than carbon. And these oxygens have those lone pairs there. So, we know the carbon is more likely to be a positive, whereas the oxygen is more likely to be a negative. Now, similar concept with these two. And we know our sulfur from earlier likes having the 4 bonds. Okay? And that gives us those extra electrons. And so it's going to be more negative, more positive. And we can check on our chart as well. So here's our oxygen, here's our sulfur. So oxygen is more negative. So that's how we know that sulfur is going to be more of a positive in that case. Okay? And don't forget the other trick that we learned as well. That if it has those extra electron pairs, it is more likely to be the negative portion of the polar. It's basically like a plus minus magnet sort of a thing. Okay? So, we have our iodine and bromine. And I'm going to make a copy . So we don't have to scroll so far. There we go. Okay. We can see our iodine's down here, and the bromine's above it. So bromine, we know, is going to be more negative. Sorry, not bromine. Beryllium. It's going to be more negative. Okay? And we can also do it with our numbers here. We have that 1, 2. We have that 1, 2, 3, 4, 5, 6, 7, and 8. Okay? So this one will have 3. Okay. This one likes it 7. Okay, so this one's happy. Whereas this one is not. Remember the octet rule. In this case, it is happy this way. However, it's missing 2 of its 4 spots. Okay? And when we're missing electrons, we are negative, which fits as well with it being more negative compared to an iodine. Or, sorry, no, this is bromine. Yeah. Ignore everything I just said for this problem. However, that is the right kind of concept. So this is, in fact, going to be that more negative compared to an iodine. However, this kind of bond rarely ever happens. So what we're actually looking at is bromine. And when we go back, you can tell that bromine's more electronegative than iodine. Sorry, that should have been so much simpler and so much easier. But the concept I explained before is still the same kind of a thing. So now, we have our oxygen, Our hydrogen, we already know oxygen has its bonus electron groups. It doesn't have another bond, so it is actually has a bunch. So if you remember, oxygen is 6. 1, 2, 3, 4, 5, 6. That's 7. So it has an extra one. When you have an extra one, in this case, you would be negative, and your hydrogen would be more positive. And looking at our table, that fits us well. Hydrogen's over here, oxygen's over here, so oxygen's more electronegative. So now, carbon and fluorine. We know carbon, that's its 4 bonds. And fluorine, that's its 7 bonds. But we can also see on this chart that going this way over, it's more electronegative. So that fluorine is more negative than this carbon. Okay? Now, nitrogen and carbon they are also in the same row, so you can also compare those. So nitrogen is more negative than carbon. Okay. And in this case, carbon, well, it's the same molecule. Okay? So it's actually nonpolar. Alright. We're getting there, I promise. Alright. So this one is the increasing polarity. So, polarity of a bond increases as the difference in the electronegativity between the bonded atoms increases. So, the greater the difference, the greater the polarity. Okay, so what it's referring to is, where does it land on this list? See now, hydrogen's way over here compared to oxygen way over here. So we know hydrogen's going to be a lot more positive than oxygen, and oxygen's going to have a lot more negative. Okay? So, the bonds we're looking at is hydrogen, chlorine, a hydrogen and oxygen bond, a phosphorus and a hydrogen bond, and a carbon and fluorine bond. Okay? So, if we go back up here, well, our hydrogen to a phosphorus. Okay. And that is only going to be 1, 2, 3, 4 steps. Okay. Now, if we do our hydrogen and our chlorine, we can see that it's going to be 1, 2, 3, 4, 5, 6 steps. Okay. Now we're doing hydrogen and oxygen. So that's going to be 1, 2, 3, 4, 5 steps. Then we have our carbon for our fluorine. That's 1, 2, 3 steps. Okay. Now, that shows you how well the steps are over here. Now, what you have to look is how many extra points does it get for bringing more up in this corner. Okay? So down here would be, it gets a +1, +2, +3, +4, +5, +6, +7. Okay? Because as you're going up, you get more electronegative. Okay? So this helps us set it up this way. Now we're doing it this way. So, our hydrogen to our phosphorus. Okay? So that is 1, 2, 3, 4, 5. So it gets +5 to it. Now chlorine, same line, a +5. And oxygen, though, gets a +6. Our fluorine also gets +6. Okay? So final count would be 9, 11, 11, and 9. Okay? Now, as you can see, we have some ties here. So how do we figure it out? Okay? We already looked at these ones. Well, let's see if they lose any points for being over here. If they're more this positive side. Okay? So in that case, with hydrogen being way over here, and it's the first column, we're going to do -1. Okay? I'm going to get rid of this extra around here. Okay? Now a chlorine. Oh, wait, I did that wrong, sorry. It's going to be the opposite. That's going to be -8, okay? Now a chlorine. Okay? -1, -2. It only loses 2 points. Wait, sorry. No. Our hydrogen also makes it lose. I'm sorry. We are looking over here. These guys. Sorry. So, 1, 2, 3, 4, 5, 6, 7, 8. So it will lose 8 points. Okay? Same thing with our hydrogen and oxygen, because it's a hydrogen, minus 8. And our chlorine. Okay? With our carbon, it's only 1, 2, 3, 4, 5. Okay? It only misses 5. Alright? So that would give us the final number of 1, 8, 9, 10, 11, 3, 3, 4. Okay? So now we know what our least amount this is our least amount of polarity. This is our greatest amount of polarity. Okay? So we know that one is going to be our least amount. And this one here is going to be our greatest amount of polarity. So the biggest difference. Okay? So of course, we have this tie here. Well, the way you can look it back, how many points did that first section get when you were going upwards? Oops. How many points got more? It's going to be this oxygen one. I got 6 points added compared to the 5 points. Okay? So then we know this oxygen is going to be bigger with its polarity compared to this chlorine. Even though this chlorine is right here and oxygen is right here, as it goes up, it gets even more negative. So we know this one and this one are different. Okay? So because it has the higher points, the oxygen one's going to be even more. And that chlorine is going to come right behind it. Now, this doesn't work for all of them. For all of the pairings and everything you can think of. But it is helpful in doing it, because it's a faster way than going through doing all of its electrons and everything like that. Okay? Because if we did it with its electrons, so like this HP, it is and our phosphorus is right here. So one's 5. 1, 2, 3, 4, 5. Okay. Now, we have our chlorine. It has that one bond. And it has the 7 electrons. So these two are stable. Okay? So we know there's not going to be as much polarity with it because they're all happy. Okay? They got the number of electrons they need and the number of bonds they need. So they're happy. So we know that they're going to be less compared to our oxygen or fluorine carbon. So if we do our hydrogen and our oxygen, well, we know this one is going to be that negative. Okay? And now, carbon and fluorine. Fluorine likes it 7. And carbon likes its 4. However, to follow this octet rule, you would have to put all of them on there. Okay? That's just for a single way. However, carbon doesn't like this, okay? Carbon's like, no. So whenever a carbon is mixed with the fluorine, it always takes all 4. Hold on, I'm reading this wrong. It is water, and it is a seed. Okay. Hold on just a second. Okay. So we have our oxygen. Yes. There we go. That makes more sense. Okay? And then we have our carbon with its fluorines. And we know okay? That's how they actually look. Sorry. So we know this side's going to be bigger. This side's smaller, positive, more negative. But it's only going in one direction. Okay? And it's really only up here that's really big. This carbon, however, it's going to be all nice and huddled in with his buddies. However, having 4 different ones in one spot, like this, is going to make a huge cloud out to each one because it needs to cover those electrons. The electrons make it really huge. So in this case, you have 4 ways that it's going compared to its 1.5 to kind of way. Really, it's just that 1. So that's why explaining with electrons that this is the most polarity, the CF one. This water is next because you know this one's going to be more positive. This one's going to be more negative. Okay? This chlorine is happy with its. Okay? And this phosphorus is happy with its. Okay? I know it's much more confusing that way. And that is why I like the little number trick I got taught. Because it made so much more sense. Okay? And it's basically just rating where it's at on the table. And that's what helps with it. Let me erase things. Okay? So we have our final answer here. So we know it's going to be that HP then the chlorine, then the oxygen, then the carbon. Okay? And hydrogen is the most common bond out of everything. Basically, everything's connected to a hydrogen in a structure. And so you know that it is a lot more stable compared to like a carbon. And so that is why you know this one has less polarity as well. Because this is more natural to have a hydrogen connected to it compared to just a carbon connected to it. And so that's how you get more of that change, more of that magnet kind of a thing, compared to just having that natural hydrogen on there as well. Typically, if it's just with natural hydrogen, it's going to be a lot lower polarity compared to something, two other things together. Alright. Naming things. Always so fun. I actually really hate them. So, this is actually also used up above this concept. When it is a covalent bond, you get like the di, tri, pent kind of a thing with an "ide" as well within the name. Compared to if it's ionic, you could just name the normal thing and have an "ide" on the second portion. Okay? That is actually an "I." So in this case, we know that's phosphorus. There's 3 of them. So we know it's tri. And then that's iodine. Tri. Iodide. Because you add on the tri and the ide. Okay? Because we know this one's going to end up being stable. So, arsenic. This is chloride, chlorine, and it has 3. So, arsenic has that 3, so it would be tri. And we would spell chlorine. But this last little bit gets turned into that ide. So, arsenic trichloride. Okay. In this next case, this one here, they are not balanced, basically. Okay, so we have that phosphorus and we have that sulfur. As we keep scrolling up to our table, we have that phosphorus and that sulfur. It needs 5 and 6. Okay. So we know with this one, it It's not going to be balanced at all in any form with this. So it's definitely a covalent bond.
What?
It is definitely a covalent bond. And so what ends up happening, and plus since this isn't all connected together, we're going to add that number amount in front of this phosphorus and the number amount in front of the sulfur. And the sulfur is going to get that "ide" added on. So in this case, it's going to be tetra. That's the 4. And of course the compound. Phosphorus. We have that 3. So tri. And then we have that sulfur. So we have sulfide, because we add on that IDE. Okay? In the case of this one here, they do eventually balance out. So we only need to really worry about the fluoride. And because they are connected to 2 different things, it's not all coming off one, we don't need to add in the 6. So it's just going to be aluminum fluoride. Okay? Because it ends up being that iconic one. Okay? It ends up following this iconic rule. Okay? In this case, because they're not all connected together, it's going to be that more covalent bond. And so you're going to have that 2 and that 5 in there. And this one has that "ide" on there. So you get di, nitrogen, pent, oxide. Okay? This one is similar to the arsenic one we've already done. Okay? So we already know arsenic. And then it's just knowing what that 5 is. It would be penta. So penta chloride. Okay? Now, going the opposite direction, we have silicon, which I don't remember the formula for silicon. So that is sulfur, that is selenium. Here it is, silicon. So Si. Okay? So we know it's going to be Si. And then we have our chloride. So we know it's chlorine. And we have tetra. So it's going to be 4. Okay? So we know sodium. And anytime you see this hydride kind of a thing, it means basically just a hydrogen is added onto it. So hydride is hydrogen. So antimony was a really weird one. It's an SB. Okay. So you get SB. Then you have your fluoride. And you can see it has that 5. Okay? Same thing with osmium. It's a weird one. It's an OS. So you get your OS. You know it is oxygen because oxy. So oxide. And then in some cases, if there is a vowel in that second portion, it won't add the A after it. And so it's just the T-E-T-R instead of the T-E-T-R-A because of this vowel. So this is 4 in this case. Okay. So now we're on to acetone. And that is C3H6O. Okay. So we know there's 3 carbons. So we can start there. We know they're all connected to each other. We have to do 2 different ones. Okay. So we have an oxygen to move. And of course that can only go on 1. So we're just going to put it, let's put it here on the end. Okay. And in most cases, a carbon likes to do a double bond with the oxygen. Okay. And now we have 6 hydrogens. Well, this one can only get 2 more. This one can get 3. So right there is 1, 2, 3, 4, 5. And number 6. Okay. And then if we just put this oxygen on this other side, it'd be the exact same thing, just flipped. So this is one of them. The only other difference you can get in how acetone is written is putting it in the center. So we have our 4, so that's happy. And the oxygen is happy with its 2. And then we have the 6 hydrogens. So the other carbons each get 3. Perfect. So we're done with the first part. So now we want that geometry again. Okay. Well, this one here is only bonded to 1, 2, 3 things. So then we know it's going to be our trigonal planar. And over here, these ones are connected to 1, 2, 3, 4. 1, 2, 3, 4. So we know that is going to be tetrahedral. So, similar concept down here. Okay. We only have the 1, 2, 3, and then the 4. Okay. So then we know this center is the trigonal planar. And then we have our tetrahedral on the sides. Okay? So now we have more the compound kind of a concept. Okay? This is with the ionic and with the covalent. Okay? So in this case, for our example, that is sodium chloride. And for covalent, that is carbon dioxide, because it has that too. Okay? So, for this one here, you know this is calcium, and then it's chloride. This calcium is bonded to two of them. However, it is an ionic bond. Okay? So you only need to name the first one, the positive one, then the second one, and just add "ide." So, this is going to be calcium chloride. We don't need to add any di in here for 2 because it is this ionic. Okay? In the case of this one, when you draw it out and everything, it becomes a covalent bond. So in that case, we have to add in this di. Okay? So Te is tellurium. And then we have our chloride with our 2. So dichloride. Okay? So in the case of this one, we know it's going to end up being this covalent. And so we're going to do boron, the first, with that one. And then we have our fluoride. And since we have our 3, trifluoride. Okay? Now, with this one here, this is going to be magnesium and sulfate and oxygen. This one, you kind of just have to memorize this, what this symbol means, because you can't really go off any of like these other ones, because it does have the 3 different compounds. Let's see, it has 1, 2, 3. Okay? This one you kind of just have to memorize it as that magnesium sulfate. Okay? These next 3 will follow it. Okay? So we have this one here. Potassium and oxygen. Okay? It ends up being an ionic bond. So we're going to get potassium oxide. This one here, we have a phosphorus and a fluoride. It ends up being a covalent. So it's going to be phosphorus 3. So it's trifluoride. Okay. This one's a little trickier. We have our iron, we have our fluoride. However, it's not the fluoride that's connected to all of them. It's the iron that has a connection to each of the three. And it's a really weird rule that comes from the covalent kind of concept. But it's also a concept with the ionic. It's one of the just those other kinds that you really have to sort of memorize it because it's written weird. So you would write the iron and you have fluoride. However, with the way it's written in actual chemistry, it has a 3 within it. Okay? Because in other ways, you would have something like that. Well, its name is exactly the same. Okay? I don't know if this is the right compound, but it's the easiest way to show you. So the name would be the exact same. Okay? The iron fluoride, iron fluoride. However, this one only has 2. So in reality, it would be iron 2 fluoride. So that's why that one has that 3. And I know there's a way to do it around this. I don't remember what though. It's easiest just to memorize that with its name. And so it's kind of just a thing to do. Okay? So, I do believe, yep, that is all of them. So that is going through the rest of that chapter 4 worksheet. So that way you can get that done and understand it, at least from the perspective that we understand more. And so, come on. Thank you. And so I hope that helps you. And there you go.